Welcome to my YouTube channel. In this channel, I'm going to discuss integral equations. Integral equations sometimes arises in solving a real-world problem. You first start by defining integral equations. Anyone can define integral equation as an equation that involves integrals. Alright, but the true definition of an integral equation is saying that an integral equation is an equation in which the unknown function, that is y of x, appears under one or more signs of integration. Okay, let's continue by considering the general form of an integral equation. Let's consider the equation below. Y of s equals to f of s plus lambda integral from a to b k of st y of t dt. We are saying that this is an integral equation because this y of s our known function, and this name y of s appears under the integral sign. So this makes this equation to be an integral equation. In naming the part of an integral equation, this part f of s is termed as the free term, and this function is always a known continuous function. That means when they give you the equation, this function is always known and it's also continuous. Okay, this sort of equation is known as the investigative parameter. This lambda is introduced. That is the investigative parameter is introduced to check the variation of the problem. If lambda is allowed to vary, the solution may not exist for a first value of lambda. So the solution may exist if the lambda is allowed to vary. Now let's move on to this part. The a and b are just the limits of integration. Now this part of the equation is known as the kernel. The kernel is known. It's a known continuous function which is defined in a square. That is, r is a is less than s, which is less than b, comma a is less than t, which is less than b. We are having our kernel to be k of st in the st plane. So if you are seeing defined in a square, let's try to use diagram to explain this. So let's have our st plane. So let me say my s plane is here, I have my t plane here. Now here is from a to b, so I have my a here and then b to here. I have a and b, I have my a here and then b to here. Now if I draw a straight line, and a straight line here, and another straight line, you see that there is a resulting square here. This is our square. In this square, this is a place where I see that the kernel is defined. K of S. So these are the parts of the integral equation. So we just move on by tackling some examples of integral equations. Examples. We are saying that this equation is an example of integral equation because first, if we check our known function, which is y of s, This same y of s appears under this integral sign. So this makes this equation to be our known function. And this is our free term, which is the f of s. It's our free term. And from this lambda is the investigative parameter. And so this is introduced to check the variation of the problem as this lambda is allowed to vary. And from 0 to s is the limit of integration. Our kernel becomes, the exponential function becomes our kernel, t of st. So this is an integral equation. Let's consider our last example, our next example. In this our next example. This is also an integral equation. We are having the unknown function which appears under the integral sign. Yeah, since the unknown function appears under the integral sign, it makes this one to be an integral equation. And the limit of integration is from 0 to 1. Lambda is the investigative parameter here. And s cubed divided by 2 is the free term or the forcing term. The kernel becomes what? St. So this is also an integral equation. So let's continue by considering an application question. In this application question, we are going to derive integral equation from a real world problem. How to derive an integral equation? How we come about integral equation when solving a real world problem. In this problem, we will look at an RC series circuit. So this is our question. This application question we are going to look at. The question is saying that consider the RC series circuit diagram and use it to derive an equation for current. Now we are having our E of t here. This is the EMF, the VR, which is the voltage across the resistor, and the voltage across the capacitor, which is named as the VC. Now let's start by solving. So the first law I'm going to consider is by Kirchhoff's voltage law. It's saying that the ET is equal to VR plus VC. Let's name it as our equation 1. And then we come to this side, which is the resistor. It's in governed by Ohm's law. So by Ohm's law, we have our VR to be equal to I of t R. Let's name this to be equation 2. Now this is a capacitor. Now you can mathematically the capacitance is given us. VC. Let's make this VC the cellular equation. Then we're going to have our VC to be equal to K K of t over c. And let's name it our equation 3. Now, current, mathematically, current is also giving us I of t is equal to dq dt. Now we have to find for what? The charge here, which is the q. So let's multiply each term by what? The dt. We're going to have our I of t dt, which is equal to what? D what? Q. Now let's integrate both sides of the equation. Now let's integrate from t naught to a certain t. So for better communication, let's change the t's here to, let's say, s. So I of s, which is what if we integrate here, I'm going to get what? Q of what? T. So our Q of t is equal to this. And let's name here as our equation 4. Now, you're having Q of t here. Now you have to substitute this equation 4 into this equation 3. So substituting equation 4 into equation 3, we're going to have our v of vc to be equal to 1 out of c integral from t naught to t I of s ds. Let's name up this equation as our equation 5. Now we now have we now know for VR, we know for the VC. Now let's substitute all the equation 5 and the equation 2 into what? Equation 1. So substituting equation 2 and equation 5 into equation 1, we're going to have E of t to be equal to, our VR is giving us I of it r plus this. Plus 1 over c taken from t naught to t I of s ds. So this is the equation I'm going to have. E of t is equal to I of t r plus I 1 over c taken from t naught to t I of s ds. Now let's make our I of t a standard equation. I'm going to have I of t r to be equal to, we move this one to the other side. So we're going to have U of t minus 1 over c integral from t naught to t I of s ds. Now let's divide each of the term of the equation by what? This r. Then I'm going to have our I of t, which will be equal to, so this time divided by r, E of t divided by r minus 1 over rc equal from t naught to t I of s ds. So you can if you compare this to the general form of integral equation, which is giving us y of s equal to f of s plus lambda a to b k of s t y of t t. You could easily see that I of t is our known function, because in this same I of t is found under the integral sign. So this makes this equation an integral equation, which is what? Which is the equation for what? For the current. And this part of the equation, U of t divided by r, is also known as for the free term, which corresponds to this side, or it's the same as for the forcing term. And the investigative parameter also corresponds to what? This side. 1 minus 1 over what? RC is our investigative what? Parameter. So it is introduced to check the variation of the problem. And the t naught to t is the what? Limit of integration. And the kernel Q of st is 1. So our K of ST in this equation is equal to 1. Is equal to 1. So this makes this equation to be an integral equation for current.